everybody, welcome back to math class. This is Miss Sharp teaching you about populations and inferences. So in the last lesson we talked about why it was important to have a random sample and have questions that were unbiased. So what's the point of all that? So what can we do with that data? So once we know we have good data, we can actually use it to make inferences and draw conclusions about a population. So go ahead and hit pause, create a new entry in your notebook, or just grab any old piece of paper if you've parted ways from your notebook. Put the title, Proportions and Inferences, and our essential question is, how can you use proportions to make inferences about a population? All right, so it's really hard to sample the entire population of something. Like if we want to know about all the lions in Africa, it's really hard to track down every single lion. But by looking at a sample, we can make a guess or prediction about the bigger population. But how can we actually do that? So here's an example. Medina wants to know about everyone's favorite sport at her school. She surveyed 50 people and 20 people said their favorite sport was basketball. If 700 kids go to her school, predict how many people in the whole school would say basketball is their favorite. Well, it's hard to cruise around and ask all 700 people about that, but we can actually use a proportion. So we can put the survey on one side. The survey and the sample are pretty much the same thing. And then we can put the entire population on the other side. So for example, she surveyed 50 people total, and 20 of them said they liked basketball. That was their favorite. So here's our sample over here. 20 out of 50 say basketball. So we want to know how many out of 700 like basketball. And then we have a proportion that we can solve where we do the whole, loopy-loop butterfly thing, and we get 50x equals 14,000. And then we would just divide by 50 on both sides to get a final answer. So when we do the math, we find out when we divide by 50 that x equals 280. So we can predict that about 280 students out of 700 will say basketball is their favorite. So is that completely accurate? Like if we did track down all 700, would we find exactly 280 liked it? Probably not, but it's a pretty good prediction based on the sample, and it's a lot easier to ask 50 people than it is 700 people. All right, so go ahead and hit pause and copy all this business down in your notes. All right, let's look at what it says. So we're going to use the data from samples like we talked about in the last lesson to make a prediction about the entire population, and we're going to do that using a proportion. So here's our little frame that we're going to fill out. So the x is going to move around. I'm just warning you that right now. But we're going to put the sample on one side, part over whole, and we're going to put the population on the other side, part over whole. And then we're going to cross multiply and solve for x, which is our unknown. Okay, so I'm going to do one more example before we add some to our notes. A shipment to a warehouse consists of 3,500 iPhones. The manager chooses a random sample of 50 iPhones and finds that 3 are defective. How many iPhones in the shipment are likely to be defective? So I'm going to set up my proportion here. I'm going to put my sample over here. So what do I know about my sample? My sample is 50, and I know that 3 are defective, and I want to do part over whole. So I'm going to say that 3 out of 50, that's my sample. And now I want to know about the whole population. Okay, so my whole population is all the iPhones, is 3,500 iPhones, and I want to know how many out of that are likely to be defective. So there's my proportion. So then if I cross multiply, I get 50x right there. 3 times 3,500 is 10,500. And then I solve by x by dividing by 50 on both sides, and that gives me a final answer of x equals 210. So that tells me out of those 3,500 iPhones, I can predict that 210 of them are going to be defective. All right, so normally if this was class, I'd have this printed out for you and you would add it to your notes. So what I want you to do is just write number 1 and just write down the highlighted parts of number 1. I gave you like a shortened version. Okay, so just number 1 and the highlighted parts. Hit pause, make that happen. Okay, so now let's take a look at number 1. It says, a manufacturer fills an order for 4,200 smartphones. Again, just write down the highlighted part. I tried to shorten it up for you. The quality inspector selects a random sample of 60 phones and finds that 4 are defective. how many smartphones in the order are likely to be defective. All right, so we're going to set up the proportion together. So right underneath what you wrote for number 1, I'm just putting it down here so there's actually room for stuff. Okay, we're going to put the sample on this side. So our sample is 60 and 4 of those are defective. So we want to do part over whole. So we're going to go 4 over 60 like this. And then we're going to put our population on this side. So our population is 4,200 smartphones, and we want to know how many out of those are going to be defective, are likely to be defective. So we're going to set it up like this. And we're trying to find the part. Okay, once we have that, we're going to cross multiply. We're going to get 60x, and we're going to find that that equals, when we go 4 times 4,200, that's 16,800, and then we can go ahead and finish the problem from there. All right, so to get x by itself, divide by 60 on both sides. That cancels this out, and then we're left with x equals 280. So we can predict that 280 of those 4,200 smartphones are going to be defective. Okay, now go ahead and hit pause, and you're going to write down example 2 here, just the highlighted parts to make it easier for you. Okay, now that you have that written down, let's take a look at it. We're going to set up a proportion again. We're going to put our sample over here, our population over here. Well, it starts with the population, so I'll just start there just to kind of make it a little different. Maybe that makes more sense to you. So I have my 4,500 elk on this side, and then I have a sample of 50 elk, and 8 of them are infected. So this is what scientists do a lot because they can't catch all the elk in a place, or all the deer, or all the fish, or whatever. So they just get a little sample, and then they use that to make an inference about the whole population. So our x is right there because we want to know how many out of the whole population. So then from there, we're just going to cross multiply and solve for x again. All right, when I cross multiply, I get 50 times x, which is 50x, 8 times 4,500, which is 36,000. I divide by 50 on both sides to get x by itself, and that gives me an answer of 720. So go ahead and make sure you pause and copy all that down. All right, so later on in the week, you're going to be asked to do some IXLs. So I screenshotted a couple IXL problems. They're really long, so again, we're going to shorten it up and just do the little parts, so you can not have to copy all this down. So go ahead and write the number 3, hit pause, and copy down just the highlighted parts. Okay, now that you got that written down, let's set up a proportion. And again, you really need to actually write this part down because when you get to the IXL exercise, if you just write down the proportion, it will not help you. Okay, so now these are a little bit different. It says there's been an epidemic amongst the prairie dogs. Trisha is a scientist who studies how diseases spread and wants to estimate the size of a particular prairie dog town. So she wants to know the whole population. First, she catches 28 prairie dogs and tags them. These prairie dogs are released, and at a later date, 290 prairie dogs are caught. Among these prairie dogs, 14 are tagged. To the nearest whole number, what is the best estimate for the prairie dog population? So we actually want to know what the population is based on the sample. All right, so we start here with the 28 prairie dogs. That's actually not the sample. We know that out of all the prairie dogs, 28 of them have tags. 28 of them are tagged. Okay, later on, now we have our sample. 290 prairie dogs are caught, and among that sample of 290, 14 are tagged. So go ahead and take a second and copy down this. And then once we have that, we can go ahead and do our cross-multiplying business and solve for x. Or another thing we can see is if there's an easy relationship. So how do we get from 14 to 28? Hopefully you can see that, oh, okay, I can times by 2. And so we can actually times by 2 down here and get our answer that way. So if we multiply by 2, that gives us the final answer of x equals 580. So go ahead and hit pause and write that down. And if that did not make sense to you, you can also cross multiply like this and get 14x equals whatever, and divide by 14, and you'll still get 580. So that tells us that there's 580 prairie dogs total because it's really hard to count all of them. All right, let's do example 4 here. So copy down a 4. Copy down just the highlighted stuff to make life easier for you. So hit pause and make it happen. Okay, let's look at the problem. It says, some researchers needed to estimate how many catfish were in a local river. Because how the heck do you count all the catfish in a river? That's like impossible. So they marked 650 catfish with tags. Later, the researchers trapped 480 catfish, of which 48 had tags. To the nearest whole number, what's the best estimate for the catfish population? So again, we want to know the population. That's X, okay? We know that they marked 650 with tags. They just went fishing. Every fish they caught, they threw a tag on it, and they did 650 tags. All right, then later on, we get the sample. Later on, they trapped 480 catfish, and 48 of them had tags. To the nearest whole number, what's the best estimate? So you might see the relationship here already, like 480 and 4,800, okay? 650 and what would this be here? So hopefully some of you can see that like, oh, I would just, like this is 10 times bigger than this, so this must be 10 times bigger than this. And that would make it 6,500. But if that does not make sense to you, I'll also do the cross multiplying way. Okay, so if I cross multiply, I get 48x. I multiply that, I get 312,000. And then I divide by 48 on both sides, and lo and behold, I get x equals 6,500. So that means there's 6,500 catfish in that river, approximately. So pause and copy this part down if you need to. All right, so what if they don't give you an exact number in a sample, but a percentage? So just watch me on this one. It says, based on a sample survey, a tutoring company claims that its students have a 48% probability of passing their classes. Out of 300 students, how many would you predict to pass? All right, we're still going to use a proportion here. And we're going to look at our entire population of students is 300, and we want to know how many out of that population would be expected to pass. And 48% is actually our sample. And percent means per 100. So that's actually 98 over 100, like that. So I can cross multiply and do that, or I can look for an easy relationship. Is there an easy relationship between 100 and 300? Yes, you times by 3. So I can go 98 times 3, and I can get 294 if I do that. And again, if that easy relationship thing does not make sense to you, just go ahead and cross multiply and you will still get the correct answer. All right, last one for our notes. So go ahead and hit pause, write down the number 5, and just write down the highlighted stuff to shorten it up. Okay, so let's get going on this one. It says, based on a sample survey, a weight loss company claims 76% of the people that join their company, like Weight Watchers or something, lose weight. Out of 550 people, how many would you predict would lose weight? So again, let's set up our proportion. And the sample is 76% of people. And how do we write 76% as a fraction? Percent means per 100, so it's 76 over 100. So there's our sample. And then it says out of 550, how many would you predict lose weight? So that means 550 is our whole population of people, and we want to know how many would lose weight. There's not really an easy relationship here, so we're going to have to do the whole cross-multiplying thing. All right, so if I go 100 times x, I get 100x. If I go 76 times 550, I get that number. To get x by itself, I divide by 100 on both sides, so that cancels out. And when you have zeros stacked on top of each other when you divide, they actually just cancel out. And 418 over 1 is just simply 418. So we would predict that out of 550 people that signed up for Weight Watchers, 418 will lose weight based on our sample. Okay, now it's time for a whiteboard. If you actually have a whiteboard, grab one. Who knows, you might have one at home. If you don't stress about it. Just grab any old piece of paper. You know, you could just find like an old worksheet out of your back pocket even and reuse that. So let's make this happen. So it says a manager samples the receipts of every 5th person who goes through the line. Out of 50 people, 4 had a mispriced item. If 600 people go to the store each day, how many would you expect to have a mispriced item? So I want you just to start by hitting pause and writing the proportion. Don't even solve it, just write the proportion. Okay, take a look at the proportion. Here's our sample, 4 out of 50, and we want to know how many out of 600. So hopefully your proportion looks like that. So now go ahead and pause again and try solving for x. Pause. So take a look and see how you did. Did you cross multiply and get that? Divide by 50 and you should have gotten that. Or you could see like 50 times 12 is 600 and 4 times 12 is 48. However you solved it, I'm just happy that you got it right. And if you didn't get it right, don't beat yourself up. Just figure out what your error is so you can get this next one right. So give yourself a little tally if you got it right. All right, next one. Jerry randomly selects 20 boxes of crayons from the shelf and finds that two boxes with at least one broken crayon. If the shelf holds 130 boxes, how many would you expect to have at least one broken crayon? So go ahead and pause, and just write your proportion. All right, so hopefully this was your proportion. 2 out of 20 is our sample, and we want to know how many out of 130. So again, pause, figure out the answer. All right, let's see how you did. So you could cross multiply and get 20x equals 260, divide by 20, and you get 13. Or you could also see that, like, how do you get from there to there? You'd times by 10, so what times 10 equals 130, and you could get it that way as well. So if you got it right, if you came up with 13 as your answer, give yourself a tally. All right, I'm going to move on to a couple of these examples like you're going to see in IXL. It says, Mary's a scientist who works at the Department of Agriculture. In order to ensure a good harvest, Mary keeps track of various local beetle populations. She catches 850 beetles, marks them, and releases them. Then later, she catches 700 beetles, 35 of which are marked. To the nearest whole number, what's the best estimate for the beetle population? Well, we want to know the whole population. So let's start our proportion. Go ahead and write that down. We want to know the whole population. Okay, that's our X. Okay, she marked 700 beetles. She originally marked 850 beetles. Then later, she caught 735 had marks. So you have 850, 735, and X. Go ahead and pause, think about it, and just fill out the proportion. All right, how'd you do on setting up your proportion? So X goes here because that's our total population. 850 goes here because she marked 850 out of all the beetles. Our sample is over here. She later caught 700, and 35 of them had marks. So if you messed up your proportion, don't beat yourself up. It's tricky. Just go ahead and cross it out and write this one. And then hit pause, and solve for X. All right, let's check in on how you did. So 35 times X is 35X. 700 times 850 is this business here. Divide by 35 on each side to get X by itself, and you should have gotten 17,000 beetles as your answer. All right, let's try one more of those IXL ones. It says, Professor Harrington's research group wants to monitor the trout population in a local stream, so they marked 700 trouts with tags. A week later, they captured 440 trout and noticed that 20 of them had tags. To the nearest whole number, what's the best estimate for the trout population? So again, here's our numbers. We have the 400 that they marked, the 440 that they later caught, 20 of those had tags, and we want to know the best estimate of the trout population. So go ahead and pause, just write the proportion. Okay, how'd you do on your proportion? We want to know the total population, so that's our X. 400 out of the total population have tags. Okay, our sample's over here. Later on, a week later, she caught 440 trout, and of those, 20 had tags. So now you can pause again, pause, and go ahead and solve for X. Okay, let's see how you did. So 20 times X is 20X. 440 times 400 is that. Divide by 20 on both sides to get the X by itself, and you should have ended up with 8,800 trout. That's a whole lot of fish. So check in with yourself. You should have tried 4 examples on your whiteboard or your scratch paper or whatever, and see, like, how many did you get right out of 4? And what was the biggest issue for you? Are you still struggling with how to set up the proportion? Are you still struggling how to solve for X? And also, don't try to do these by hand. Make sure you have a calculator around. Okay, you can always open up another tab in your browser and use a calculator. So please do not try to do these the long way. All right, so that's pretty much it for me. There is going to be a little video after this. So you know what? Let's do the video first and then we'll come back to the summary. So here's an example of how scientists use this basic sampling technique in real life. Oh, hold on.
In your area, I'm going to show you now how you might figure that out.
Counting wild animals.
Back here enjoying the cold.
Getting ready to spotlight some deer.
Of course, we're not just enduring the cold for the fun of it.
We're doing this to count the wildlife.
Well, definitely some deer.
Raccoons and bears, who knows what else will fly out there.
But first, let's step back and look at some of the basics of sampling. Now understand this, the number of individuals in an area doesn't just magically appear. You have to physically count them, and sometimes it's not all that easy. Plants are a little bit easier because they stay in one spot. But even with plants, I've actually only been to one place where they've counted every single plant in an area. That was in Panama. They counted, tagged, and measured every plant over a certain size in a 50-hectare plot. Now, the problem with that is that it took forever. But there is an easier way. It's called sampling with quadrats.
Sampling with quadrats.
So by randomly putting quadrats out into a field, you can get an estimate of how many plants are in a certain area. Of course, this technique doesn't work so well with animals that move, and that is where other techniques come in handy, like mark and recapture.
Mark and recapture.
Now, a couple of years ago, we did this with sharks in Hawaii. You see, as long as you can identify individuals, which we did with a video camera, you can use some simple math and come up with a population estimate. But since we're actually not identifying individual deer here, we need a slightly different technique.
We're counting deer tonight with the distance sampling method.
Distance sampling.
So the spotlighters are looking for the eye shine of the deer, so it's going to reflect back the light, and hopefully it will be fairly easy for them to see.
In this method, you basically drive transects through an area, and then you count the deer with spotlights. Now, this works pretty well, as long as you take into account a few things.
Most of the deer will be close to the road, and as they get further from the road, the probability of us seeing them will get less and less.
And that means that most of the deer we count will be near the road. And as the deer get further away from the road, we'll count fewer deer. Now, knowing the exact shape of that graph helps to estimate the number of deer in the area. But the real purpose of this project is to compare these estimates with a new technique they're using, camera traps.
So we want to compare what we're getting right now with our camera traps with this sort of old school method of distance sampling.
Camera traps.
Camera traps are one of Roland's specialties. He's helped coordinate camera traps all over the world. And part of the reason they're so great is that the animals hardly notice them. And they're using these camera traps to help answer a bigger question.
We're running them in areas that have hunting and don't have hunting, and then at areas at different distances from the trail, so we can see how does hunting affect the wildlife community, and then also how does hiking affect the wildlife community.
And that just happens to be one of the cool things you can ask when you know how to estimate the number of animals in an area. Now, if you're interested in distance sampling or camera traps, then I encourage you to watch the full explanation of how this works by Roland himself, right here.
And of course, if you like what we're doing, watch more of our videos.
All right. So now let's finish it up with the summary. So I want you to, pause, take some time, read over the notes, look at your examples, and write about how we, answer the EQ. Look at how we can use samples to make inferences or find things about the population. And the point of the summary is show what you learned, show what you know. Okay? So make sure when you're all done, you take a picture and you go ahead and send it to your teacher by texting them or emailing them. All right, hope you enjoyed the lesson. This is some real life math here that scientists do all the time. And I'll see you next time in math class. Bye.